Rotational inertia. So, as a review from last semester, what property of matter resists change to the motion? Well, it was inertia. And how did we quantify it? Mass. This should be a review. We did this fairly early last semester, just after we finished kinematics. So, what is resistance to change in rotational motion? Unsurprisingly, it's rotational inertia. So it's really the same concept, except we put the adjective there so we know that it's a change in rotational motion that it's resisting. And how do we quantify this? Well, we all know that it's not just the mass of something that matters to how hard it is to rotate it. If I have something that's got its mass spread out, it's going to take a lot more effort to rotate it than something that has the mass concentrated all in one point. So we call this moment of inertia. The symbol for it is a capital I, so this is one of those where it's not all Greek to me. And the definition of this is we sum up the mass times the radius squared of each little chunk of material in the object. And so this is a three-dimensional sum, which really you need calculus to really understand. But if you just think of each little piece has its own little moment of inertia, and it's going to resist a change to rotation, when you add them all up, they have even more resistance to changing rotation. And the units coming from that definition are kilograms meters squared. So a quick note here, if I have a point mass, all I have is one single chunk, so I can use mr squared. This is not going to hold true for all other shapes. Here are some of the other shapes you might see. This is straight out of the OpenStax book. All right, so for various shapes, and depending on which axis they're rotating about, you're going to have different equations. So the only one here is also mr squared, is a hoop rotating about its cylindrical axis, because all the mass is at the radius, so you can essentially think of this as a circle of point masses. The other ones, so you can see the rods or the cylinders are going to have different equations. Here, capital M always means the total mass, and we assume that these are all uniform density in the bits that are there. The thin spherical shell is essentially just a very thin shell, so if the hoop is considered to be infinitely thin, so is the spherical shell. So they're complicated. You need calculus to derive them. You do not need to memorize them. All right. If you were given a solid sphere and set it rotating, so say like the Earth, you would have to treat it as uniformly dense, and then you would be given the equation I equals 2/5 mr squared. And therefore, you would be able to plug that in, solve for I, and use that somewhere else in another equation. As a quick summary, here are some comparisons of the translational concepts to the rotational concepts. In both cases, the property that objects have that means they resist changes to their motion is inertia. In rotation, we just add the adjective. In translational motion, we quantify that inertia as the mass, because the actual physical size doesn't matter, just how much stuff there is, all right, how much inertia it has. However, in rotational inertia, we quantify it as moment of inertia, which maybe makes it a little easier to remember in this case, I don't know. And in both cases, we don't know calculus, all right? So for translational motion, we use center of mass and treat things as a point mass for most of our problems in introductory physics. In rotational motion, we don't know the calculus, so we get the equations, but the mass distribution, otherwise known as the shape, does matter when we're considering how difficult it is to change the rotational motion of an object.